This is the final video of chapter 5. In the last video, we talked about read and write quorums and how leaderless replication works. In this video, we'll see two new concepts, sloppy quorum and hinted handoffs. We'll also see a few algorithms to detect the concurrent writes and how to merge the concurrent values. So databases with appropriately configured quorums, they can tolerate the failure of individual nodes without the need of any failover process for the leader node. Now they can also tolerate individual nodes going slow because requests, they don't have to wait for all the n nodes to respond. They can return when when the W or R nodes, which is needed for a quorum, they have responded. So these characteristics, they make databases with leaderless replication very appealing for use cases that require high availability and low latency, and also which can tolerate occasional stale reads. However, quorums, as we described so far, they are not as fault tolerant as they could be. A network interruption can easily cut off a client from a large number of database nodes. So in this situation, it's likely that fewer than W or R nodes remain, so the client can no longer reach a quorum. So in a large cluster, it's likely that the client can connect to some database nodes during the network interruption, but not to those nodes that it needs to assemble a quorum for a particular value. So by that it means it's not able to reach out to the home nodes for a particular value. So in that case, the DB designers, they face a trade-off. So the first one the first thing to do is to return errors to all the requests for which we cannot reach a quorum of W or R nodes. Or the second thing is that we can do is to accept the writes anyway and write those values to some other nodes that are reachable, but they are not among the n nodes on which the value usually lives. So they are not among the home nodes for that particular value. The second solution is known as sloppy quorum. So in a sloppy quorum, the writes and reads, they still require W and R successful responses, so the quorum condition still holds, but those may include nodes which are not among the designated n home nodes which is needed for a value. By analogy, if you lock yourself out of your house, then you may knock on your neighbor's door and ask whether you may stay on their couch for temporarily. So this is what we do in case of sloppy quorum also. We temporarily place it on some other node that's not the home node for that value. Now once the network interruption is fixed, then any writes that one node temporarily accepted on behalf of the other node, they are sent back to the appropriate home nodes. So this process is called hinted handoff. By the same house and key analogy, once you find the keys to your house again, your neighbor will politely ask you to get off their couch and then go home. So sloppy quorums are particularly useful for increasing the write availability. As long as any W nodes are available, the database can still accept the writes. So however, this means that even let's say your W plus R greater than N, this condition which is needed for quorum, that is satisfied, you cannot be sure to read the latest value for that key, because that latest value, it might have been temporarily written to some nodes which is outside of N, so which might not be the home node for that value. In that case, if you try to read, then that might return a stale result for you. So sloppy quorums, they are optional in all common Dynamo implementations. In React, they are enabled by default, and in Cassandra and Voldemort DB, they are also disabled by default. We have discussed cross datacenter replication as a use case for multi-leader replication. Now leaderless replication is also suitable for multi-datacenter use case, since it's designed to tolerate conflicting concurrent writes, network interruptions, and also latency spikes. Cassandra and Voldemort DB, they both implement their multi-datacenter support within the normal leaderless model. So the number of replicas n, it includes nodes in all the data centers, and in the configuration, you can specify how many of the n replicas you want to have in each of the data centers. Now each write from a client is sent to all the replicas regardless of the data center, but the client in this case, it will only wait for acknowledgement from a quorum of nodes which is there in its own local data center, so that this will be totally unaffected by the delays and interruptions on the cross data center link. So the higher latency writes to other data centers, they are usually configured to happen in an async way. Now Dynamo style databases, they allow several clients to concurrently write to the same key, which means that the conflicts will occur even if strict quorum conditions are used. The problem is that events can arrive in a different order at different nodes due to variable like network delays and partial failures. So for example, this image it shows two clients, client A and client B. They are simultaneously writing to a key X in a 3-node data center. So R1, R2, R3 are the 3 replicas here. So the client A is setting the value of X to A, and here the client B is setting the value of X to B. Now node 1, it receives the write from A, but it never receives the write from B due to maybe a transient outage. So in this case, if client B is trying to send this request, so this node is not responsive here. So node 2, it first receives the item from A and then it receives the write from B. Now node 3, it first receives the write from B and then it receives the write from A. So this write from B is earlier and then this write from A is received. Now if each node it simply overrode the value for a key whenever it received a write request from the client, then the nodes will become permanently inconsistent as shown in the final get request that is made. So node 2 thinks that the final value of X is B, whereas these two nodes, node 1 and replica 1 and replica 3, they think that the final value of X, it should be A. So in order to become eventually consistent, the replicas, all these 3 replicas, they should converge toward the same value. So how do they do that? So one might hope that the replicated databases would handle this automatically, but unfortunately most implementation, they are quite poor. So if you want to avoid losing data, so the application developer, they need to know a lot about the internals of your database's conflict handling. So we have briefly touched upon the conflict resolution in all the chapter 5 videos till now. So let's see how it will really work. So one approach for achieving eventual convergence is to declare that each replica, it only need to store the most recent value and allow all the older values to be overwritten and discarded. So but this idea will work as long as we have some way of like unambiguously determining which write is the most recent. So we can enforce an arbitrary order on them. For example, we can attach a timestamp on each write and then pick the biggest timestamp as the most recent and discard any writes which has an earlier timestamp. So this simple conflict resolution algorithm is called last write wins, and this is the only supported conflict resolution method in Cassandra. So last write wins, it achieves the goal of eventual convergence, but at the cost of durability. So if there are several concurrent writes which are being made to the same key, then even if they were all reported to be successful to the client because they were written to W replicas, only one of the writes will survive and the others will be silently discarded. So there are some situations, for example, caching, in which the lost writes are perhaps acceptable, but if losing data is not acceptable, then this last write wins. It's a poor choice for conflict resolution. So the happens before relationship, it's a way to determine if two operations are concurrent or not. If we can capture the happening order for a given bunch of operations, then we can also look at a way to merge the concurrent values in those. So an operation A, it happens before operation B if in some way B knows about A, or it depends on A, or it builds upon A in some way. For example, if B, it wants to, let's say, modify the value which A has already written to the DB, then we can say that B happens before A, or there is some kind of causal dependency here. On the other hand, when two clients, they start the operation, let's say, and if they don't know that the other client is also performing an operation on the same key, so there's no causal dependency between these two operations. So in this case, we can simply say that these two operations are concurrent because neither happens before the other in this case, and neither of these clients, they know about the other client. So in this case, we can say that there's no happens before relationship and they are concurrent operations. Let's take a look at an algorithm that determines whether two operations are concurrent or whether one happened before another. So this also demonstrates how the concurrent values are merged together. So this image here, it shows two clients which are constantly concurrently they are adding items to the same shopping cart. So initially the cart is empty, and these two clients, they are unaware of each other, so they don't know that the other client is also adding items to the same cart. So let's take a look at the flow of the operations here. So client 1 here, it adds some item milk to this cart. Now this is the first write to that key, so the server will successfully store it and assign a version number 1. Now this server, it also echoes the value back to the client along with this new version number. Now client 2 add a new item which is eggs in the cart, so it does not know that the client 1 has already added milk, so it thinks that eggs is the only item which is there in the cart. So the server will then assign version 2 to this write, and it will store eggs and milk as two separate values. It then returns both of these values to the client along with the new updated version number, which is 2. So client 1, now this is not aware of client 2's write, so it wants to add a new item which is flour to the cart. So it thinks that the current cart contents, it should be milk and flour. So it sends this value to the server along with the version number 1 which the client 1 previously received. So in this case the server will merge the values that it already has, and it will return new version number which is 3 to client 1. Now meanwhile the client 2, it wants to add ham to the cart. It's unaware that client 1 has already added flour. So client 2, it received the two values, milk and eggs, from the server in the last response. So the client will now merge those two values, and it will add a new item which is ham to form a new value. It will send this value to the server along with the previous version number that it has, which is 2. So the server will respond with a updated value and also a new version number which is 4. Now finally client 1 wants to add bacon, so it previously received milk, flour and eggs from the server at version 3. So it merges those values, it will add bacon to the server, and it will send it to the server. Now the server will merge all the values that it has, and it will send the updated version number 5 to the client. Now the example in the last slide, it only used a single replica, but how will this algorithm change when there are multiple replicas but no leader? So the last slide, it used a single version number to capture the dependencies between the operations, but that is not sufficient when there are multiple replicas accepting the writes concurrently. So instead we need to use a version number which is per replica and as well as per key also. So each replica increments its own version number when processing a write, and it will also keep track of the version numbers that it has seen from all the other replicas. So this information will indicate which values to overwrite and which values to keep. So this collection of version number from all the replicas is called a version vector. So like the version number in the last example, version vectors are also sent from the database replicas to clients when the values are read, and they need to be sent back to the database when a value is subsequently written. So this version vector, it allows the database to distinguish between overwrites and the concurrent writes.